So I'm going to be using as much colors as possible with shapes and curves. So at least you can give me the same amount of awe that you just gave Alexa. So you let me know at the end. Thank you, Alexa, very, very much for making my life so easy now. So what I'm going to be trying to tell you today is that we do, or we can, and we will, cure cancer. So the way I'm going to just go on a global level of how we think about this is two ways. One is, can we treat cancer and cure it? And second, can we prevent cancer? There are major impediments to this, and there are major solutions to that too. So just to give you an overview of how cancer developed. So cancer, in essence, cancer is a genetic disease. What happened in the cell is something happened to the DNA of any cell, and it gets damaged. The damage in the cell can happen because of many issues or many reasons. One of them could be smoking. The second could be sunlight. The third could be anything that we don't know of. And when that happens, our normal cell, which is usually develop proteins, those proteins can exist within our system to make our function or our cells work functionally well. When that mutation happen or the event happen to the cell, it leads to the development of completely new proteins within the cell that make our cells work berserkly. So they're not properly managed anymore. They're not properly dividing and quiescing or sitting down, but rather what happens is they grow beyond what they should grow. That's cancer. Now, with that in mind, what happens then is when they grow, they flip, they leave, they go somewhere else, to the lung, to the brain, to the liver, and this is how we die. Because we take over the normal function and our system collapses. So to cure cancer, first, how to cure cancer and how to prevent cancer. There are two systems that we really need to work on to be able to get there. The good news is that the incidence of cancer and the mortality of cancer has been dropping in the United States. And I repeat, in the United States, for the past 10 years, 1% per year. So we're making major progress in that. That's not enough, of course. And when you look of why we were able to do that, at least until recently, is one, and the major cause is we stopped smoking. So smoking in the US went down from almost 52% into now around 17% amongst adults. Mind you, I'm talking a lot US, and I'm underlying that US because I'm going to talk to you about the next level of what happened global fight against cancer. But here's what we've done, at least in the cure of diseases, particularly in the cure of cancer. This is a disease that's called chronic myelogenous leukemia, which is CML. It's one of the deadly diseases. It's a leukemia, it's a blood cancer. This is how people used to die from, and we're talking about chemotherapy, and we're talking less than in the 1970s or mid-1970s. This is what happened to the disease in the past 50 years. If that is not progress, I don't know what progress is, but currently, we cure a majority of those patients because of development of new drugs that were dependent on our knowledge of what happened to the genetic system within our cells. This is another disease, which is acute lymphocytic leukemia, which is a very deadly disease in kids. And when we were kids, we always knew our friends or some friends that got leukemia, and it was so chilling, and they died. This is 1968 to 1970 survival, and this is a year. So majority of those patients are dying within 2 years from diagnosis. This is 70 to 72. And this is what happens now. So cancer is a curable disease. We're talking about now in 2006 to 2009, this is creeping up. So almost 95% of patients, of kids with leukemia, get cured. We still believe, by the way, we still believe when we hear leukemia that it's a deadly disease. Well, it's not. Now, you need to take into account that those therapies are not easy therapies. There are lots of complications. They might have long-term complications, etc. But at least when we think about what we could do, we can do a lot. Those are small number of diseases. Majority of them are blood cancers. So when we think about, again, when we think about, now I'm going to skip those, when we think about other diseases, like diseases which are what we call solid tumors, not blood diseases, and this is a disease called melanoma, which is a skin disease, very common, extremely common in the United States and outside the United States. This is the survival of melanoma when we treat with chemotherapy. And this is a slide from 10 years ago, actually less than 10 years ago. If you look at this, 80% to 90% of those patients that have melanoma that's metastasized, they die within a year. That's 2010, 2011. Okay. So what happened to science? I showed you one that we could cure for a long time now, at least in the past 50 years, blood diseases, some of them at least. Second, I showed you at least an example of a disease in solid tumors that's deadly, and majority of the diseases in solid tumors are deadly. So if I showed you some of those slides in 2010, 2011, 2013 even, of lung cancer, melanoma, etc., you're going to see it all like that. So what happened? There's a field called immunotherapy that started mainly at the National Institutes of Health, or NIH, in Bethesda in the late 1980s, early 1990s, although it has a longer history to it. But I'm going to take you a little bit through the history, but first to show you one thing. This is cancer cell. These are our immune cells. We know for a long time that those immune cells can come and attach to our cancer cell. That's a long science. We've observed it, we knew it. And not only can recognize it and come attached to it, but can literally dig a hole into the cancer cell and get the cancer cell to completely disappear. That's something we knew. But no one knew how to harvest the immune system, our own immune system, to make this work. A science started at NIH and other places, but mainly at NIH, to start seeing how can we do that. Well, I'm going to go back to what I showed you before. Something happened to the normal cell. It accumulates new proteins, and those new proteins make the cell cancer cell. Well, we know that those proteins can present on the cell surface of our cells. So if they can present on the cell surface of our cells, can we make the immune cells recognize them and kill them, particularly that they are foreign, they're not normal. And we know that our immune cells can understand that there's something called foreign, like virus, like bacteria, and they can recognize it, they can kill it. So can we do that with cancer? And can we lead to the development of something that would recognize those, because all our protein in our cells can present themselves out. So if they can present themselves out on our cells, including cancer cells, and we know that our immune system can come and recognize them and can dig a hole into them, can this infected cells, rather than being a virus, be a cancer? And those abnormal cells that occurred because of smoking or because of sunlight or because of anything, those normal protein can be recognized by the T cells. And this is where we started a field called cancer vaccine in the early 1990s, early to mid-1990s at the National Cancer Institute in Bethesda, Maryland. So the principle of this, since we have a mutation, those normal protein become abnormal, they present themselves. We know that immune cells can recognize abnormal protein on the cells. So can we develop a vaccine that if we vaccinate, like what we do with virus, like what we do with flu, can we teach our immune system to recognize the flu virus as abnormal and kill it when we give the flu virus vaccine or the measles vaccine or etc.? Can we do the same thing for cancer? So in principle, if we can identify those in cancer, and then we can vaccinate the patient, and we can generate those immune cells, then the immune cells can be activated, they go to the cancer, and they can kill it. That was the principle of how we started immune therapy to a large degree. I'm going to take you in history. So vaccine. So when we think of vaccine, it's not something new. This guy is from this land, from the UK. His name is Edward Jenner. So what he did is he published a book in 1798 about vaccines for measles. For chickenpox. And what he did, in his book, he wrote what he did. He said, I selected a healthy boy, and he literally did. What Edward Jenner recognized is that the dairymaid in the UK, they don't get smallpox. And the reason they don't get smallpox is because when they milk the cows, they have cowpox on their hand. So they get cowpox from the cows. But they never get chickenpox. So what he thought of, if I take those cowpox and inoculate people with it, would they be resistant to smallpox? And can we prevent them from having smallpox? So this is what he did. He selected a healthy boy, about 8-year-old, and that healthy boy was a son of one of the dairymaid. So he tried to do the experiment on it, and he vaccinated that in his boy, and then 3 months later, he inoculated that boy with smallpox to see whether the boy would die or not. I assure you we can't do that now. It's impossible to do that now. The boy was lucky enough, and he survived. This is the consent process, by the way. This is how they consented the boy to be able to get it. So what he did afterward, he inoculated 13 others with the same, and the 13 survived. This is how vaccines started. And by the way, the word vaccine comes from vaca, and vaca means cow. So this is how it all developed. So we thought of the same thing for cancer. So what we did is, we actually wanted to vaccinate patients with those proteins that we can identify on their tumors and lead to the development of immune cells that could treat tumors. So we did the first clinical trial ever at NIH, where we took a tumor from a patient. We looked into what kind of abnormality this has in certain genes. We make the vaccine, and we vaccinated the patient. This was the first patient we vaccinated. This is a guy with colon cancer, metastasized to the lung, and had no treatment at that time. We took part of that lung. We understood what are the changes that happened within the patient, and we vaccinated them against that patient, against those changes. And 3 months later, that's gone. And not only that, we actually found that the patient had liver metastases or liver masses. We took them out. They were all necrotic. They're all gone. That was early 1990s. So what happened since then? What happened is that when we did that, we proved that this worked. However, only one patient responded. So there were lots of things that we needed to understand. So what we did is, since then, we really understood lots of things. That tumors had lots of things within it. Tumor is a very bright creature. Lots of things within it that inhibit those immune cells. So I have 3 seconds and then I stop. 30 seconds? Okay. So 30 seconds and then I stop. You don't have to show me the 15 seconds. Is what? You're sure? May I? May I? Okay. All right, I'll continue. But I will promise not to continue for long, though. I'll tell you part of that story. All right, so what happened is, tumor is a very, very intelligent and bright creature. It knows how to tell those guys, get off. and it suppressed them. And these are some of the mechanisms of why, if we give a vaccine, we generate this, they come to the tumor, well, they're going to be looking at a lot of enemies, and they're going to die. So in the past 20 years, we understood a lot about this. And why we understood a lot about this? Because of the major biotechnology revolution. In 1990s, there was a press release, press conference, President Clinton with two of very bright scientists, Francis Collins and Venner, which they showed that we can sequence the human genome. We sequenced the human genome. It took $13 billion in 13 years when we sequenced the human genome in the 1990s. So what happened to this technology? A lot of things happened to this technology. Biotechnology developed, bioinformatics, tremendous amount of changes in engineering. And what happened is, today, actually in 2015, we can sequence a whole human genome within 24 hours with $700. We're talking about 20 years. Today, this dropped now to almost $400. So that's major revolution. When you think about the human lives and the human span of thousands and thousands of years, this is a revolution that happened only within the last 20 years. When I was a postdoc at NIH, in 1990 I started my postdoc. I worked on trying to find, you remember those that I showed you, the difference between those? I tried to identify one of them. It took us almost 2 years to sequence it and make it happen. Today, my postdocs can identify 30,000 of them overnight with the technology that we have. So these are some of the technologies, called microarray technology and others, deep sequencing, etc. So the technology literally bolstered. With that in mind, we were able to identify lots of those. And when we identified lots of those, one of them showed, one of the mechanisms was identified by this guy. His name is Jim Allison, who's a very good friend of mine. And this is another brilliant scientist. His name is Phil Greenberg, that works on TCL. Identified one of them, which is called CTLA-4, that when the cell comes to bind to the tumor, it binds to it here. It's called CTLA-4. It sends the negative signal. It kills it. So I identified this, and he developed antibody to block it. And then another guy identified another molecule, which is called PD-1. So that happened also in the early 1990s. When that happened, they developed antibodies to block them. So when they blocked those antibodies, we took them into the clinic, and they went into the clinic in 2010 in clinical trials. Remember that melanoma thing that I showed you? This is in 2010, survival. This is now. So in 10 years, this is today. As a matter of fact, this is today. We haven't reached this yet. This is expected. This is today. It was presented in a meeting 2 weeks ago at ESMO. It's called ESMO. That now survival of melanoma after less than 10 years because of those two drugs is 50%. So we're probably curing 50% of patients today. And this is only in less than 10 years. This is the example. President Carter had melanoma 4 years ago. When I was director of the cancer center in Georgia, I was called on this. And it not only he developed melanoma, it went to his brain. Brain cancer, particularly melanoma, you should be dead in 4 months, 6 months at max. This guy is still building houses after 4 years, 4.5 years, because he received that therapy. Now, this led to a major revolution in medicine, and probably one of the major revolutions in the past 100 years, which is called immunotherapy. And it got a Nobel Prize last year. One thing I should tell you that we talked about this, in the 1990s, no one believed us, and no one thought it can happen. And we were almost a mockery of science. That immunotherapy will never work. I talked to the table yesterday. I told them I had a friend who was with me at NIH. We were sharing We were sharing an office for 10 years. He used to come 15 minutes before me every day. He was a pharmacologist, work on chemotherapy. I knock on the door, come in and say, "Good morning, Chris." And he says, "Good morning, are you still working on immunotherapy?" Every day. We were doubted all along, and now we know that this happens. And by the way, Chris now is a chief medical officer for an immunotherapy company. So just an FYI. This is not the whole story. Immunotherapy works. However, it doesn't work for all patients. People are still dying in some diseases, actually in lots of diseases. Immunotherapy works currently in some diseases very well, but in general, if you take all cancers, around 15 to 20%. So there's lots of work to be done. Some of the work is to understand this more, but we are at the tip of the iceberg. And as an example, we just found why lots of patients do not respond, and we published this just last month. And we identified a reason of why they don't respond and how we can change some of the non-responders to responders. And we're doing this in clinical trials. The only reason I'm showing you this is because lots of improvement and lots of things are coming. There's at least 500 new compounds of immunotherapy will be coming to the clinics within 5 years. So can we cure cancer? The answer to that is yes, we absolutely can cure cancer. And I think this is something that, I don't know why this is it, and I think this is something that we will see very, very shortly within the next 5 years. Thank you very much.